So today we're going to be talking about algebra, and I chose to do logarithms. So yeah, this is usually a topic that shows up a little bit on AMC, but mostly on AME. But the problems that show up aren't like, a lot of them are not super hard. So I guess we'll just go over like the basic properties of logarithms first, and then we'll go through some problems. So the first one that we have is log base b of a product is the sum of the logs of those two numbers, x and y. And then similarly, if we have a product, instead it's just going to be the difference between the logarithms. And this rule actually comes from if we combine the first one with the power rule, which says log base b of x to the p equals p times log base b of x. So if you plug in like p equals 1 or -1, and x equals y, and then you multiply x by 1 over y, then this is what you're going to get. And then we also have change of base. So if we have log base b of some number x, we can also express that as log x over log b, where these two logarithms are in any base that we want. They just have to be the same. Okay, so this was probably review for some of you, but those are pretty much all of the like rules or things that you need to know about logarithms before being able to solve these problems. So the first one is, yeah, this problem. And I think we're just going to go ahead and do it right now because it's not super hard. So we have the value of x that satisfies this equation can be written as m over n, and then we want to find m plus n. So here, one property that is like useful is log base, let's say a, sure, of b is always going to be equal to log base a to the n of b to the n. And this comes directly from the rules that we just went over. So we have that log base a to the n of b to the n is equal to log of b to the n over log of a to the n by change of base. And if we use the power rule now for the n's, we can bring them down and then make them coefficients. So this is equal to n log b over n log a. And then we cancel out the n's. So we're left with log b over log a. And then using change of base, but like reversed, this is equal to log base a of b, which is what we wanted. So this is true. And the way that we can use this to solve this problem is that we see that 3 to the 20 and 3 to the 20 are very similar, but the only difference is that 3 to the 20 equals 3 to the 20 to the 101, because 20 equals 20 times 101. So we can use the rule that we just looked at and say that if log base 2 to the x of 3 to the 20 equals log base 2 to the x plus 3 of 3 to the 20 to the 101, that means that 2 to the x plus 3 has to be equal to 2 to the x to the 101. and this is just 2 to the 101x. So solving x plus 3 equals 101x gives us x equals 3 over 100. And so our answer is 3 plus 100, so 103. Okay, so that wasn't so bad. And it just uses a few of those properties that we just looked at. Hopefully that made sense. And we'll move to the next one. So here we have a positive number x that's neither 1 over 20 or 1/2, satisfies log base 20x of 22x equals log base 2x of 202x. And we want to find what this value is, which is also equal to this value. And that's going to be log base 10 of some rational number. And then we find m plus n as before. So this problem, since we have just one value that we're looking at and we're interested in, we can call this value y. And from now, all we have to do is just interpret these logarithms. So log base 20x of 22x equals y means that 20x to the y is equal to 22x, and then similarly 2x to the y equals 202x. And we see that these expressions and equations are very similar, except that the constants are different. And so we can divide one by the other, and we'll be left with mostly just constants. So if we divide the first one by the second one, we get 20x over 2x, which is just 10 to the y, is equal to 22 over 202, which is 11 over 101. And now we're pretty much done because we just wanted y, which is both of these expressions. So everything equals y, and then y is just going to be log base 10 of 11 over 101. So m plus n is 112. Yeah, so as you can see, like these problems, just knowing the very basic rules of logarithms gets you pretty much as far as you need to go. Yeah. Okay. If there are any questions, please ask, but otherwise we will move on. So this problem is actually from this year's Amy. It was very early, I think like number 2 or something on Amy 1. But yeah, we have a positive real number b that's not equal to 1, and then also another positive number n. And we're given that they satisfy these two equations. And we're finding the value of n. So I think I'll give you maybe like 30 seconds to just try it by yourself, because it's a little bit more involved than the first two. Okay, so the first thing that we're going to do is, let's just look at the first equation first. So we have log base b of n, the square root of that is equal to log base b of root n. And we know that square root n is just n to the 1/2. So using the power rule, this gives us 1/2 log base b of n. And since we're seeing so many like log base b of n's everywhere, we're just going to substitute a new variable to make it less writing and also just simplify our equations. So that means square root of x is equal to x over 2. And we can solve this already, so squaring both sides, or actually we don't have to square both sides, we can just divide by root x on both sides, gives us square root of x equals 2, so x equals 4. Okay, now we can use the second equation, so b times log base b of n, which is just x, is equal to log base b of b times n. And now we're going to use the product rule, which is basically we can split up these two terms in the product here. So log base b of b plus log base b of n. And we know log base b of b is just 1. So we get 1 plus log base b of n, which is x. So we're seeing like the x's come up everywhere, and eventually all of our equations are only in terms of x instead of both b and n. So yeah, we already know that x is equal to 4, which means that we can find b from bx equals 1 plus x. So b equals 5 over 4. And finally, we're asked to find n. So this equation gives us n equals b to the x, which is 5 over 4 to the 4. So 625 over 256. And then adding the numerator and denominator just gives 881. Okay. So this next problem is actually from an AMC, and I don't think I meant to put the answer choices there, but I guess they're there. So I'll give you a little bit of time, maybe like half a minute to a minute to just try it. Okay, let's go over this problem. So we have real numbers a and b, where square root log a plus square root log b plus log of square root a plus log of square root b equals 100. And all of the logs are in base 10. We also know that all 4 terms in the sum are positive integers. and we're asked for the product AB. So here we can pretty much already tell that there's going to be a lot of like powers of 10, and also the fact that all of these terms are integers helps us a little bit because the answers are going to be nicer that way. So the first thing that we can do is just take the same rules that we used before. We know that a is, or square root a is a to the 1/2. So we have 1/2 log a and 1/2 log b. And one thing that we can do is we know that square root log a is an integer, a positive integer, and that means that log a itself has to be a perfect square and an integer, obviously. And same thing for b, because everything in this equation is symmetric. So we know that log a is a perfect square. And we also know that 1/2 log a is an integer. So let's say that log a is equal to x squared for some positive integer x. Then that means that x squared over 2 is also an integer, which means that x has to be even. So let's say x is equal to 2m. Then we have 1/2 log a is 2m squared. And then this is 4m squared. And then this same thing applies to b. Yeah, so similarly, we have log b is equal to 4n squared for some integer n, and 1/2 log b is 2n squared. So then rewriting the equation that we have using m and n instead, square root of 4m squared is 2m, and then square root of 4n squared is 2n, and then we have 2m squared plus 2n squared. And all this is equal to 100. So we can factor out the 2. We get m squared plus m plus n squared plus n, and then 2 times 50. So we get that m squared plus m plus n squared plus n is equal to 50. And now, since we know that m and n are both integers, there are like very limited values, or a very limited number of values that n squared plus m and n squared plus n can be. We know that m squared plus m in general, actually, do we know that? We know that m squared plus m and n squared plus n have to add up to like 50, which means that each of the terms have to be at most 50, like on their own. So that means that we're going to get m and n have to be relatively small. And it turns out the biggest they can be is 6, because if you have either of them at least 7, then the whole sum is going to be way too big. So we just have to kind of list out like the possibilities for what this sum can be. So m squared plus m or m squared plus n can be 1 times 2, 2 times 3, 3 times 4, 4 times 5, or 5 times 6. And this is 2, 6, 12, 20, and 30. And we pick the two that can add up to 50, and immediately we see 20 and 30 work. So that means that we have m and n are equal to 4 and 5 in some order. And we're asked for AB, which means that we want 10 to the 4m squared, which is 4 times 16, times 10 to the 4n squared. So this is 100 plus 64, so 10 to the 164. And that's D. Okay, cool. Next problem. This one is also from an AMC, and I'll give you a little bit of time, but we're running like kind of low because I have 2 more problems. But yeah. Okay, sorry, that wasn't a lot of time, but we're going to keep going. So here we're just going to use the same methods as we did before, just looking at the different properties. So one thing that we can immediately see is this looks like a lot of powers in both the base and the term that we're taking the logarithm of. So we have like k and k here, and from what we proved before, we can just take those out. So this is equal to log base 9 of 25. But we also realize that 9 is 3 squared, 25 is 5 squared, so we can take out the like squared exponents as well. So we're left with just log base 3 of 5, which is really nice. So this whole term, the second one, is just a sum of log base 3 of 5, but 100 times. So we get 100 log base 3 of 5. And for the first term, it's a little bit more complicated, but we're going to get log base 5 to the k of 3 to the k squared. And we can take out an exponent of k in both of these, both the bottom and the top. So we just get log base 5 of 3 to the k, since 3 to the k equals 3 to the k squared. And using the power rule, we get k log base 5 of 3. So if we're summing this thing over 1 to 20, first of all, we can just take out the constant log base 5 of 3. So we're just summing like 1 plus 2 plus all the way to 20 times log base 5 of 3. And the formula for that is 20 times 21 over 2. So this is 210 times log base 5 of 3. We just need to multiply, oh sorry, not those two. This one and this 100 log base 3 of 5 together to get our answer. So we get 210 times 100, and then log base 5 of 3 and log base 3 of 5, if you use like change of base, they're just going to be reciprocals of each other, so they multiply to 1. So those two terms cancel each other out, and our answer is just 21,000. Yeah, that's a pretty nice problem. It's very neat. And the last one that we have is kind of difficult. It's like in late AME, but I think I'm just gonna start going over it now so that we finish on time relatively. So we have a Martian civilization where all of the logarithms are base b, and then we're going to, yeah, we have these two equations and we want to find what that base is. Okay. Actually, this was not the one from like later maybe. I had another one, but I don't think we will get to it. So yeah, I can show you it at the end, but I won't go over it. So for this one, we're going to first look at the second equation because it's a little bit simpler. We have, by change of base, log x over log x. X is this term, and then log x is here, is equal to 54, which means that log of x is equal to 54 times the log of log base b of x. So then we can just express x in terms of the numbers that we have here. So x is going to be equal to log base b of x to the 54th term, since we're taking this up into an exponent and then getting rid of the logs. Yeah. Now we have log, or from the first equation, 3 log base b of square root of x, which is log base b of x to the 27th, times log base b of x equals 56. So this product is just log base b of x to the 28th, which gives us 3 log base b of log base b of x to the 28th equals 56. We can bring this 3 up into the exponent, and that gives us log base b of log base b of x to the 84 equals 56. Okay, so now we want to kind of use this expression for x that we have and plug it in a couple more times. So what we want to do is change this 84 into a 54. And the way that we can do that is if we think about like taking this exponent down, we can make the exponent on top 54 if we multiply log base b of x by 54 instead. So this is just going to be 56 times 54 over 84. And luckily, this turns out to be a nice number, and this is 36. So this thing is equal to log base b of x to the 54, and this is x. So log base b of x is equal to 36. So that means that log base b of x to the 54 is equal to 36 to the 54. And now again, we see this x term, and we get like exactly what x is. Since 36 is 6 squared, this is just 6 to the 108. And we want to find b, where b is, or sorry, x is equal to b to the 36. So 6 to the 108 equals b to the 36. And then taking like 1 over 36 exponent of each side, we get b equals 6 cubed, or 216. Okay. Actually, this part that I got here didn't need all of this. You just take it from the second equation directly, like log base b of x to the 54 equals x. But yeah. Okay, I hope all of that made sense. I can show you this one really quickly. And the basic idea of it is to get like a bunch of terms where you have n to the n equals some constant. And then n is going to be like expressions in terms of like the log base a of a bunch of things. And then you can solve for n directly. And I think you do this 2 times until you can find what x actually is. Yeah, so that is all for me. I think Nicole will take it from here.